Francine decides that she wants to use solar power for her house. She meets with Mr. Not Honest. He tells her that he has a new device to get electricity from the sun, and it gets heat from focusing sunlight on a spot on the side of the heat engine. It outputs to a cold reservoir that is at the air temperature of 20 degrees Celsius. He claims that it is 60% efficient. What temperature does the sunlight coming in have to be? Is this a realistic producer of electricity for Francine? Let's see. Let's look at the heat engine that's supposed to create this 60% efficiency. So first, we'll define a heat engine. A heat engine is a device where water is transferred from a hot reservoir, and this is his example of a heat engine. We have our hot reservoir here. Water is going to go from the hot reservoir to a cold reservoir, and along the way, some of the energy will come out in the form of work. So this is the heat engine itself. This is where the work gets pulled out, and then some water has to go into the cold reservoir. So we're going to assume that no energy is lost. All of it is accounted for. We're going to use some variables in our heat engine to refer to different pieces. So first we label TH. This is the temperature of the hot reservoir. We also are going to send heat down to the heat engine. And we'll call that Q sub H. Q sub H means the heat that comes out of the hot reservoir. We also have heat that comes from the engine to the cold reservoir. And we call that Q sub C. Q sub C is the heat output from the engine to the cold reservoir. The work that comes out of the heat engine is called W sub out. So W out is... We also have Tc, which is the temperature of the cold reservoir. So those are all of our pieces. Let's look at how all of these variables are related, how they depend on one another. If we assume that no energy is lost, then that means the heat that comes in has to go into either work out or heat output. The heat input to the engine equals the work out plus the heat output. We can also find what is the work output of this engine by rearranging this equation, just subtracting QC, and we get the work out is the heat that goes in minus the heat that comes out. That'll give us the work that comes out. So let's figure out how efficient an engine can be. In general, efficiency is what you get out divided by what you put in. It could be up to a maximum value of 1 or 100%. For these variables, let's replace what we get out with the work out. And work out we found to be QH minus QC. And what we put into our heat engine is just the heat in, the heat from the hot reservoir. So the efficiency of a heat engine is right here. Now the trick is, no heat engine is 100% efficient. Some energy will always be lost to the heat that comes out at the bottom. All the energy won't go into work. Some of it will have to go down into the cold reservoir. We will talk about this concept more in the next unit, the next in the next lesson, which is on the second law of thermodynamics, which explains why this fact is true. So there's another way we can look at the efficiency of a heat engine, and that is to find its maximum efficiency. The maximum efficiency of a heat engine is called the Carnot efficiency. The Carnot efficiency is this equation simplified, QH over QH minus QC over QH. In this case, because heat and temperature are directly proportional, we're actually going to have a result that uses temperature instead of heat. So the Carnot efficiency is 1 minus Tc over Th. And this temperature must be in Kelvin. This will give you the overall theoretical efficiency of a heat engine. 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Now, these two equations are not on the AP Physics equation sheet. So you should be able to understand how to get this one and how to get to this one from here. Let's look at Mr. Not Honest's claim. He said that the cold reservoir was at a temperature of 20 degrees Celsius. And we're going to get this into Kelvin. So Kelvin temperature is 273 plus Celsius. So the cold temperature in Kelvin is 293 Kelvin. He said it was 60% efficient. Let's use our Carnot efficiency equation to see what temperature the sunlight is going to have to warm the water to. Our efficiency is 60%. So if you solve for the temperature of the hot reservoir, to get a 60% efficient device, our temperature in the hot reservoir has to be 733 Kelvin, which is 460 degrees Celsius. Remember, the boiling point of water is 100 degrees Celsius. So is that a reasonable temperature to get from just concentrating the heat of the sun? That is not a reasonable temperature. This device is not realistically possible. I just want to talk about one other example. What about a refrigerator? A refrigerator is similar to a heat engine, but it's called a heat pump. The difference is, for a refrigerator, we want to move the heat out of our cold reservoir into the hot reservoir. So the picture, the layout is the same, but the direction of the arrows is different. Heat from the cold reservoir is actually going to go into the heat engine, which is the back of our refrigerator. And we're going to do work into the system. And then our heat is going to go out of the system to the warm temperature. So the equation actually looks almost the same as the heat engine. The difference is we have work in instead of work out. We still have these two added together to equal this, and the direction is different. So that's what a heat pump looks like.